Some solar energy collectors, like solar water heaters and photovoltaic panels, work with diffuse light, that is, from many angles at the same time, and are effective nearly anywhere in the world. Others require direct light and have to be located in places that have few cloudy days. They also have to aim directly at the source, which requires tracking the sun as it moves across the sky. With such stringent sighting and control requirements, you might wonder why anyone would be interested in direct solar. There are several reasons, including superior energy conversion, but they all come down to one thing. We can focus and concentrate direct light, but we have no such control over diffuse light. While standard photovoltaic collectors work better if aimed directly at the sun, the efficiency gain is not usually considered worthwhile, even if tracking is simple. But even complicated and expensive tracking can be cost-effective in the right circumstances. For example, at Nevada Solar One, hundreds of mirrors independently track the sun, reflecting the light toward a common conversion point located high above them. Direct solar conversion sighting would be simplified if, instead of reflecting light toward a distant point, each incident device would concentrate the light internally. For example, the UC San Diego Photonic Systems Integration Laboratory has demonstrated a self-contained collector in which miniature lenses focus the incident sunlight onto the surface of a flat slab light guide. At each focal point, the slab is optically punctured by modified refractive properties, allowing the concentrated beam to enter the slab. All of the focused incident light enters the slab, but only a small portion of the random beams inside the slab escape through the pinpoint puncture. The slab conducts the light to high-efficiency PV cells on the edges of the collector. The collector must still mechanically track the sun, but the overall mechanism is much simpler than something like Solar One. Even better would be a collector that could track the sun optically, without mechanical movement, not only eliminating the cost and complexity of tracking, but enabling much more flexible sighting, for example, as panels on the sides of buildings. Some researchers have proposed a concentrating slab similar to the UCSD solar collector, but with temporary optical portals created by the concentrated energy at each focus. This utilizes the ability of a lens to focus beams incident at any angle. What we normally call the focus of a lens is actually the focal point of the paraxial beam, that is, the one parallel to the lens axis. The lens produces a unique focus for every beam angle. With static tracking, as the sun traverses the sky, the beam angle changes and the focus of each lens in the collector changes accordingly. This off-axis focusing is rarely used and has not received much theoretical attention. My college physics textbook says that all the foci lie on one plane. This is exactly what the solar collector needs, but is not correct. I wrote the Octopus program to trace off-axis beams. For example, here we are tracing rays from beams at 40, 30, 20, 10, and 0-degree angles as they pass through a two-phase focusing lens. Tracing beams at multiple angles simultaneously helps us see their geometric relationship. In reality, a solar collector sees only one beam angle at a time, as determined by the sun's position. The locus of the 5 foci looks like a parabola, with its vertex at the paraxial focus, opening toward the left, or, as we modify the shape of the lens, toward the right. At the lens configuration with the sharpest foci, the foci are very far from being coplanar. As we modify the lens to improve coplanarity, the foci become fuzzy. At the best configuration for coplanarity, the locus wavers around the paraxial focus plane, with some points toward the left and others toward the right of the paraxial focus. With a sharp focus, exactly at the surface of the light guide, an entire beam will squeeze through a tiny pinhole. If the focus is fuzzy, the portal must be larger to admit all of the light. If the foci don't line up, the portal must be even larger for the beams whose foci don't occur at the surface of the guide. Octopus shows that the best that can be achieved opens up about 3% of the guide's surface, compared to less than 1% in the mechanical tracker. More light will escape the guide through these larger portals. This doesn't necessarily mean that the collector is 3 times worse overall, because this is just one of many possible sources of inefficiency. We have been looking at a two-phase lens with air between the egress face and the orthogonal light guide. A single-phase lens might afford better coupling, and in any case is likely easier to make. But Octopus shows that the best coplanarity that can be achieved with a single-phase lens is much worse than with a two-phase.